So we discussed this equation here that we use for the axial load capacity. And we said there's going to be maybe about 20%, maybe 23% difference between spiral column axial load capacity and tight column capacity. The reason because code here acknowledges the effect of adding confinement reinforcement, which is a spiral, and for that you have this 23%. This 23% is going to come in two pieces here, two items. One of them is going to be the phi factor, the 0.75 versus 0.65, and the other factor is going to be this 0.85 for the small eccentricity versus a 0.8 for tight column, come to small eccentricity. Now, when it comes to the spiral design, we said that you are going to be using this equation, and this equation here would give you the demand. So whatever is needed, this is going to be the minimum reinforcement needed for the tie itself. It's going to be given by this equation. So which equation is this again? This is here to give you the minimum needed. All right, this is the minimum needed. How about this equation? What does it give you here? It gives you the provided. So after you provide the amount of reinforcement, you can figure out how much reinforcement ratio you have added here to the column. You would like this rho S, the calculated one, based on the provided amount of reinforcement with spiral reinforcement, to be at least equal to the demand, the required. Again, I want to be sure that there is no conflict here, or there is no misunderstanding. This equation here, it gives you the needed, whatever the code needs. And this equation here is going to give you whatever that you have provided. You want this value here, this rho sub S, to be more than the minimum needed. The equation here, this is just 0.45, is going to be a constant. A sub G cross section area, A sub CH is going to be the cross section area for one chord. It's going to be the confined concrete itself. It's going to be measured to the outside of the tie itself or the spiral, not to the center line, not to the inside of the spiral. It's going to be to the outside of the spiral. F prime C is the strength of concrete. F YT is going to be the yield strength for the steel. Okay. How about this equation here? This steer ratio actually is a volumetric steer ratio. To determine this, what you need to do to find out, let's say that you're going to be taking a strip, so, or a slice if you like, you're taking this slice of the column, you figure out the volume, and then you figure out the volume of this spiral. How do you do here the volume of the spiral? You find out the length of the spiral. It's going to be pi times d. What is d in this case is going to be d to the center line of the spiral itself. It's going to be 2ds of the spiral. Times pi is going to give you the length. And then you say times the cross-section area of the spiral itself. Now you have the volume of the steel spiral. Now you divide by the concrete volume. Concrete volume is going to be equal to pi d squared, which means this cross-section area of the entire column. And then you multiply by S, the spacing that you're going to be providing the spiral within. There is a simpler way of doing it. Instead of doing this volume, which almost no one is going to be doing it this way, there is a simpler way. If you just look at this equation here, this equation shows the volume of the spiral, which means this denominator, this top term, divided by the denominator, divided by this term here. So this term here is going to be the volume of the spiral, and this term here is going to be the volume of the concrete. ds is going to be the diameter to the center of the spiral, and this dch is going to be to the outside of the spiral to find out the volume of this confined concrete. Because the difference between ds and dch is not really big, we can reduce the amount of work that we are doing here and clean this equation and make it as 4 times the cross-section area of one spiral divided by S divided by dch. So now it's going to be much simpler for you. It's going to be only 4 ASP divided by S divided by dch. Much simpler, isn't it? You don't want to do this. So please don't use this equation. This equation just for your information to understand where it's coming from. It's going to be as simple as this. Any questions? You're good? No questions? All right. Let's see this example. This example, it says, determine whether the spiral column of cross-section shown, here's the cross-section, 15-inch diameter. I have here 1.5-inch cover. Then I have a spiral. It says here 3/8 of an inch. It is unlikely that you're going to see it written like this for rebar, and usually, but this is what we have in the book, usually is going to be number 3 at 2 inches. So usually this should have been written as number 3 at 2 inch on center. This is the standard way of writing it in business or in engineering. When you practice, this is the way that you write it down. You'd never write 3/8 of an inch. No one would do it this way in rebars. Vertical rebars, it is 7 number 8. So this arrow actually should be pointing at this guy, right? Not at the spiral. So this gave me 7 number 8 rebars, right? I have 7 rebars, 1, 2, 3, 4, 5, 6, 7, and this gave me number 8. The diameter is number 8. And how much is the cross-section area for one number 8? Anyone knows? A sub B for number 8 equals
0.79.
9 square inches. Okay. So I have total of 7 multiplied by 0.79, right? So it says here in the section shown. So I went to the section, I looked at it, studied everything in there. Now I'm back to this, to the description, to the question itself, to the manuscript. It says in the figure, is adequate to carry or to support a factored axial load P sub U of 540 kips. So I guess if I have multi-story building and I'm designing this column section, I'd like here to design it right above the foundation, which means this is going to be the column supporting everything above it. So total load is going to be 540 kips applied to this column, and this already factored. It says assume small eccentricity. What does it mean by assume small eccentricity? It means simply just use this equation, because this equation consider the small eccentricity. There is no big moment added or big eccentricity added to this column. So this column here includes the small eccentricity effect. It says here, assume a small eccentricity, check the spiral, which means design the spiral. See if the spiral here is good. How can I know this? I'm going to say, okay, in this case, I need to run these two equations and compare the provided versus the minimum needed, right? And hopefully I have more provided than the needed in this example. So, okay. Concrete strength is going to be 4,000 psi. Yield strength is going to be 60,000 psi. Okay, great. So number 1, find out if this column is adequate to carry or to support this factor load of 540 kips. All right. Gross section area is going to be pi d squared divided by 4. Diameter is 15 inch. If you remember, that was 15 inch. This gives you the gross section area of the column. For the reinforcing steel, the vertical ones, I'm going to have 7 rebars times 0.79 square inch for number 8. So I'm going to say this is here for what? I'm going to say number 8. A sub B for number 8. So that I don't forget what is this coming from. It says 5.53 square inches. Okay, good. How about the C ratio? It's one of the things that you need to check in columns. It's going to be the amount of vertical C ratio. You take this AS divided by A sub G, by the gross section area. It says here 0.03. What does it mean? 3%. This should be fine. Why? Because my limit is from 1%. It has to be more than 1% and less than 8%. So I should be fine. How about the axial load capacity? I'm going to say, okay, now let me use this equation for the small eccentricity. Right? I'm going to have a phi factor of, if you remember, 0.75. And here's the equation. Just put it here. This equation includes here 2 sections. This section here, or this factor, this term is going to be for the steel strength. 60 is going to be daily trends, F sub Y. And 5.35, I'm going to say 5.35 is this A sub S, right? Multiplied by 60. How about the concrete strength? You can say concrete strength is going to be this term here. 0.85 times F prime C. So what is this? F prime C, right? Concrete strength. What is the 176? I'm going to say this is going to be the total cross-section area of the concrete column. How about 535? I'm going to say this is again AS. So what you're doing here, you're trying to find out the net cross-section area of the concrete in here, right? It's going to be in this section here. AG minus AST, which is this number here. To account for the small eccentricity, you have a factor of 0.85. Around the numbers, I'm getting an axial capacity of 583. Your demand, factor demand, is 540 kips. This is good. it is slightly larger than 540, which is great. Just go back here, confirm the 540 kips. I'm gonna say, okay, let me go back. Here is 540 kips. This is all the demand I have as P ultimate. All right. Now I'm done with the vertical elasticity ratio check, and also I'm done with the concrete strength. Questions? Nothing? We're good? All right. So next, I need to check the spiral. So let me check the spiral. DCH is going to be the diameter to the outside of the spiral, right? This is going to be the confined core. It's going to be 15 inches the diameter. Subtracting 2 times 1.5. 1.5 inch is the clear cover. So let me take you back. Here is 1.5 inch, right? The clear cover. So DCH is going to be the distance from here. Let me put it from outside of the spiral to outside of the spiral. Total diameter is 15 inch. You subtract 3 inches because you have 1.5 inch cover from each side. You have here 12 inches. So this is going to be 12 inches. ACH, cross-section area of ACH of the confined core is going to be equal to pi d sub CH squared divided by 4 is going to be 113. So then let me look for the equation for the needed spiral reinforcement ratio. All right. It says here 0.45 is going to be just a constant. I mean, nothing to do about this constant. A sub G, the cross-section area, is 176. Where do I have it? Where is this coming from? I'm going to go back one slide to look at it. 176.7. Total cross-section area of the column, the spiral column, 176.7. You divide this by ACH, cross-section area of the confined core, 113. Subtracting 1. This usually is going to be more than 1, this factor, because you take the total cross-section area of the column, subtracting the confined core, which is slightly smaller. So I know that for sure this is going to be more than 1, and this equation is going to be okay. I'm going to have a positive value at the end. Now, F prime C, as it says, is going to be 4,000 PSI concrete versus 60,000 for the CDU threads. I guess in this equation, I should be fine to say 4 divided by 60. I don't really need to say 4,000 divided by 60,000. So the critical equation that here is going to be a problem that you really need to go with PSI when you have screw to F prime C. But as long as you have F sub C, F prime C, and FYT, like FY like this, it's okay to use KSI. So this equation here, it gives me, again, the demand, the minimum amount of a spiral reinforcement ratio that I need to provide there. It says it's going to be this much. So, okay. Now let me see how much we have provided. How would I know how much we have provided? I'm going to go back here to my slide. We provided number 3 at 2 inch. So S is provided to me here. It is given, right? I'm not going to come up with it. I know it ranges from 1 inch to 3 inch, right? So it says here 2 inches. So number 1, I know this is going to be less than 3 inches. I should be fine. But you know what? The number that needs to be less than 3 inches is going to be the clear distance. This is actually center to center. This is going to be the space center to center of the spiral. But I'm going to say it should be fine because if I say here it's going to be 2 inches, right? It's going to be less than 3 inches. Also, because this is also number 3 bars. So if you like to find out the clear spacing, it's going to be equal to 2 inches subtracting the bar diameter. The bar diameter is going to be 3/81 inch. So I should be more than 1. I should be less than 3 inches, but I need also to state that. Because just by looking at it and inspecting it, by just looking at it is not enough. I need to document this in my analysis. So, okay. The clear spacing. So let me look here at the bottom first at the clear spacing. Clear distance is how much? 2 inches subtracting 3/81 inch for the diameter is going to be 1.581 inch. Less than 3 inches and also more than 1 inch, then I should be fine. Right? How about the steer ratio? The steer ratio needed is going to be 0.0169. I understand, like 1.6%. How about the provided? As I said that I have number 3 at 2 inches. So provided, I'm going to be using this equation. This is here the simplified equation that I should be able to use. So don't try to use a complicated one or the complex form. Here's a complex form. I don't want you to use this. This is just to explain it to you. If you waste your time and you try to use this, You may do a mistake in the middle. You know, usually when you have a bunch of numbers, you add more numbers to it, it's going to be most likely to make like a calculation error, you know? You don't want to do this. Just to stay with the simple form. So this can be the simple form that you want to use. Okay, good. Now let me see how much reinforcement we have provided, reinforcement ratio for the spiral. I know for one rebar, it's going to be 0.11 square inches for number 3. This is going to be AB for number 3. Let's look at here at the equation. 4 times 0.11, which is ASP divided by DCH. I have it here, 12 inches. Divided by S, the spacing, 2 inches, given to me. You run the analysis, the reinforcement ratio provided is 1.8%. Now, which one's larger? So, okay, this is good. Provided is more than this is okay. So my column is good. I'm gonna go back here. This column is good to support 540 kips, and the spiral reinforcement is good for this design. Any questions?
Can you explain how we got the value for the clear spacing? It's 2 minus 3/8.
Absolutely, yeah. Okay. Enlarge this. I'm gonna do here. Let's say I'm cutting a cross section here, right? So I'm gonna see here one spiral. Just gonna enlarge it a little bit, and here's the next one. Here's the side of the cone, as if I'm cutting section right here. Okay, looking up. The spacing from this line, which is the center of the spiral, to this line is how much? Anyone recalls? Yes? You guys recall the spacing?
Is it 3 inches?
3 inches. Is it 3 inches?
2 inches.
Is it 2 or 3? Forgot.
The S is equal to 2 inches.
2 inches. It says here number 3 at 2 inches. So S is equal to 2 inches. This is going to be S. Now I'm trying to figure out the clear spacing. What does it mean by clear spacing? It means this. Distance from here to there. Right? To here. How much is this? See, this distance here equals S minus. From here is going to be the bar radius, and from here is going to be the bar radius, right? So I'm going to say minus dB. What is dB? The bar diameter. Because you have here a radius and a radius, they're going to be adding up to 1 diameter. So, okay, 2 inches minus. How big is this rebar? You guys know? I'm going to take it back here. I'm going to say number 3. What does it mean by number 3? It means 3/8 of an inch, right? 3.75 or 3/8. Now let me go here and check. 2 minus 3/8, which means 0.35. 3.75 is going to be 1 5/8 of an inch, which is the same as this one. Are we good? Now we know where it's coming from. This number is going to be this dimension. If you like. Yes, are we good? Clear?
Yes, thank you. Yep, thank you.
No problem, no problem. More questions? No, I'm done with the spiral column. Just, you know, I went to slide number 16, so I'm done with this section. So I want to be sure that we have it covered, so that when you guys see the project, you're not surprised how you design a spiral column.
Is the max S spacing 3 inches? That's why we're worried about it being less than 3 inches.
Yeah, yeah. Where did you find this? Let me go back. Just want to confirm here. Do we have it here somewhere? Does it say maximum, minimum? You see it?
Yeah, I see it. Okay.
Yeah, it's right here. You see that? Clear spacing. This is for the clear spacing, right? Not center to center. Maximum 3 inches. minimum 1 inch. Okay,
Got it. Thank you.
we're good. All right. More questions on the spiral columns?
Professor, why did you divide the area of the concrete by 4? Is that just the 4 KSI or what is it?
Where is this at? Which slide should I go to? Here or here?
The problem we just did.
This one here.
the
Yes,
next
here's
one?
the problem.
Wait, yeah, divide by 4 or no, the previous one.
Which, this one or here?
Before that one.
This 4? This
No,
4?
like the last slide. Last slide.
Last slide. This is the last slide.
No, the one before that one.
Okay. Here it is.
Yeah, right there. So the AG divide 4, is that like the pressure or?
Here, this
is
AG,
that so the first equation on top right there.
the first
AG
equation.
instead of
Okay,
pi.
all right, I got it. Where is this coming from? All right, when you do the cross-section area of a circle, you have 2 ways of doing it. You can say pi. So if you don't mind, I'm gonna write the pi this way, right? I'm gonna say pi r squared. Am I correct? Yes? Okay. Or you can say pi times the diameter. So I'm gonna say d squared, correct? Divided by 4. So it's gonna be one of 2. It's either that you say pi r squared or pi d squared divided by 4. So now where is this 4 coming from? It's coming from this equation, right? Because in this equation, I used the diameter. I did not use the radius. Let me go back here 1 slide to make it clear to you. If you go here back 1 slide, this here's the diameter is 15 inches. All right?
All right, yeah.
All right. More questions? No questions? We're good? All right. Have you guys seen the project? Yes?
No.
All right. So let me show you the project. It's posted already. So take a second here while I'm opening the files. If you please access it. It should be under assignment or assignments. You can see this picture. It's a plan layout, a building. This is gonna be here, the building itself, right? These are the columns. And it says typical column is gonna be 16 by 16. So the architect here is telling you it's gonna be 16 by 16. It's okay if you like to make it 18 by 18. I mean, as a structural designer, right? They give me here, this is what I call here grid line. So this center line here, this is what I call here grid lines. So I have 2 sets of grid lines. Some grid lines running in the X direction or longitudinal direction. It's called A, B, C, D. And then you have 1, 2, 3 numerical is going to be running in this direction. The spacing here is standard, like 26 feet, same module. And the total building length, I'm going to say maybe 130 and fraction. Same thing for the width, 28 feet, typical. This is the standard. And then in the middle here, this is like an office building, right? So the middle here is going to be men's restroom and women's restroom. You have an elevator and a staircase. So this is what I have from the architect, right? Any questions on what you're looking at? Everything's good? Were you guys able to find out this plan online?
Yes.
Yeah.
Can you
Okay.
repeat that?
Repeat what?
I just missed the stuff while I was looking out for the paper.
Okay, no problem. I repeat it. Yes, but go ahead. Yeah, I have another question. Someone else asked the question, or I'm mistaken. All right. So looking here at the plan, is everybody now with me? Did you find out the plan online? Canvas?
Yeah, I found it.
Great, okay. So you're going to see here the project criteria. You're going to see maybe a couple of files or maybe 3 files. I'm going to be going through one by one so that you guys know what we're talking about. So the first one, it shows the plan view, the columns, and then you have the grid lines, 1, 2, 3, 4, 5, 6, and A, B, C, D. This is what you call here the grid lines. Give me a second. So just to confirm again, we have on this plan, this architectural plan, and it shows the grid lines 1, 2, 3 in one direction. And then I have it also A, B, and C, and D in the other direction. I have here the same module or the same spacing between the columns, 26 feet. And in here, it's 28 feet. So it's typical, just to make it easy for us. So that's why I don't have lots of changes. The column, the standard column size or the typical column size is going to be 16 inch by 16 inch. But if you need it to be 18 inch, we can do it 18 inch. But this is the first estimate. And of course, later on, we can change the design if we want to. We have 2 restrooms. Then we have an elevator. We have some stairs here. And then we have a wall here. And most likely, this wall is going to be a concrete wall. Just so you know, it's going to be a concrete wall in the perimeter. Okay? So this is what we have. This is going to be the architectural plan. The structure plan is a little bit different. I don't really care about this partition wall. If you see here the difference, I'm not showing here this partition walls. So concrete wall is giving the perimeter. And of course, you're going to have this 4 columns. So this here, as you see, it is shaded. So this wall is going to be all made out of concrete, and we have the same columns. Now I don't have an open space like this. Now I start to show the beams. So I'm going to say columns going to be the same, right? Here are the columns. You're going to start here to put beams going to be running in the X direction. Look at this, beam. And if you notice here that we have something called a beam and a girder. This is going to be a beam, starts here and ends here, right? This is going to be one span. But here is a girder. What's the difference? If you look here, this girder, it supports beams, right? This is why I call it a girder. And the girder is supported at the end with columns. Also, I have some of these beams, because beams here is running in the X direction, they are supported directly by the column. You see some of these beams, as you see here, supported by a girder, and some of these beams are supported directly by the column. We just dump the load directly to the column. Okay. So now where's the slab? I'm going to say the slab is going to be covering the entire area. So if you're looking here for the slab covers the entire building here, except for when you have an opening. So the staircase here, the stair itself is going to be made out of structural steel, right? Like channels and this kind of things. It's going to be right here in the middle. And it's going to be like an elevator. So elevator, you need to have an open shaft. And this area here, you're going to have concrete slab also, and beams. You see, you're going to have some beams here to support the concrete slab. So someone here is going to look and say, now, where is the concrete slab panel or bay? If I like to look at one, I'm going to say it's going to be this piece here, right? It's going to be one concrete slab piece. How much is the length of it? This length, you say length of it, let's say from the center of the column or center of the beam, if you like, which means if I extend it a little bit this way, send this little bit this way, just to get a quick answer, it's going to be 26 feet. Let's say, how about the width? How much is this length here for this direction? You say, it seems to me that all of these beams are put at equal space. So the spacing here between one beam and the other beam is going to be equal to 28 feet divided by how much? Abigail? Yeah. All right, Mateo. All right, good. So how much is this? It's going to be 9 feet and how much? And 4 inches. Does this make sense? Yes?
Yes.
Okay, very good. All right. So now I know the size of this bay here, or this panel, is going to be 26 feet by roughly, let's say, 9 feet. Just throw the number there, 9 feet. If the aspect ratio of one of the slabs is more than 2, what is the aspect ratio? I'm going to say this dimension here, I'm going to call it L. And this dimension here, I'm going to call it B. I'm going to say if L divided by B more than or equal to 2.0, we call this what? One-way slab. Are we good? How about here? Do we have L over B is going to be more than 2? Is this true?
Yes.
Yes, yes, yeah, it's more than 2, definitely. So I have here a condition of one-way slab, meaning I'm going to take this aside. Now let me look here at the load, how it is transferred to the beam. This load, half of it is going to be coming this way, and half of it is going to be coming this way. As if I can here split this slab like this, right? I'm going to say this top half of the slab of this bay is going to be supported by this beam, and this bottom half of this bay is going to be supported by this beam, right? And say, is there anything that is going directly to the girder? I'm going to say no. In one-way slab, we assume that this beam here supports this piece of the concrete slab and a similar piece from the other side, like in here. So actually, if I'd like to go to any other beam, I'm going to go here and consider this beam. I'm going to say, how about this beam here? How much it supports? I'm going to say this beam supports this part of this slab and a similar part from the other side. So it supports this tributary area. This beam here supports this tributary area of the concrete slab. So if you like to design the beam and you need to figure out how much is the load that goes to this beam, you need to find out the weight, as in dead load and live load that you guys have seen before, right? Supported by this beam, which means this area here, find out this area, multiply by the load, uniform load, to find out the total load supported by this beam. How about this girder here? Does support any direct portion of this slab? I'm going to say no. If you like to model this girder, so let's say here's a girder, you're going to do it like a beam like this, and then you're going to have here 2 supports, you know, like roller support or hinge support, and then you're going to have 2-point load that comes to it. So this here is going to be a point load coming from this beam, right? And a point load is going to be coming from this beam. So you're going to say, this is great, this is going to be coming from these 2 beams. How about this beam here? I mean, what's supporting these beams? You're going to say, well, you're going to have also a point load coming from this side and a point load coming from this side. So great, which means the structure system for this beam is going to be this beam from here to there, a support and a support, a point load coming from this side, same thing from this side, here and there. Someone's going to say, but this is not a simply supported beam because I can have continuation, right? I can provide the continuity. I'm going to say, you're right. Here is this beam for girder. It's going to have more than one support, right? You're going to have support here and a support there. You're going to have also plenty of point loads. You're going to have point load from this side, here, and here, and here, throughout the entire beam. So now I understand why I have taken the structure analysis thing. Now I guess it's going to be useful in this case because I need it. Okay. How about the slab itself? How can you design the slab itself? And say, what do you mean? I mean, when you cut a section through here, when you look at the slab itself, aren't you going to put reinforcing in the slab? I'm going to say yes. How do you put reinforcing? You say, well, reinforcing is going to be running across. So to design the slab, I'm going to be taking here a strip. Only 1 foot strip. So how much is this width? Again, how much is this? Why did they consider only? Why did they consider only a foot? Why didn't they say 5 feet or 6 feet? Any idea? Going to be taking this width here to be a foot. Why a foot? Because whatever that you provide in this foot here, you're going to be providing throughout the entire width of the building. So to make it simple, I'm just going to be taking here 1 foot for the width of the strip. I'm going to be calling this a strip. It's going to be 1 foot strip. 1 foot strip. Strip width is going to be equal to 1 foot. If I'm doing here an actual design, like in real design, real practice, I need to figure out how many strips. Let me figure out here how many strips. I'm going to say, let me copy this here, just to think about it. I'm going to say, for this bay here, I guess I'm going to have this strip is going to be running how many bays or spans? I'm going to say 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 what? I'm going to say 9 spans. So this is actually, it acts like a beam. So the slab itself is supported over beams. So it's going to be acting like a beam. And for each one of this beam, I'm going to say I'm going to have a support here if I'd like to design the one-way slab. You follow me? And I have here a bunch of supports, right? So actually the structure system of the slab is going to be one long continuous, you can say I have here support, is going to be one continuous beam supported over slabs, supported over beams. Very good. Everybody follow? So this here is going to be one strip, which represents the slab, right? Slab design. And it's going to be supported over 10 supports. So in your analysis, it's going to be one long beam. The width of it is going to be 1 foot. And the thickness, or the total depth, is going to be equal to the thickness of the concrete slab that we need to work it together, right? I'm going to say here is one strip, which is very good representative to the slab that we have in here. I'm going to say, yeah, look at this. This also is going to be the same. One strip supported by 10. Someone's going to say, how about in here, in this case? Because look what happened. All of a sudden, the beam is not continuous. Which beam? I'm talking about the slab. But when I do the analysis, it's going to be like a beam. What is the reason? Because number of spans is different. In here, I have 9 spans. In here, I have 1, 2, 3, 4, 5. And what's happening here on the top? I'm going to say this is going to be a separate beam. And how many spans are we talking about here? I'm going to say in here, we have only 3 spans. I say, how about in here? I say, yeah, this is going to be exactly the same as this. There's no difference because I don't have any interruptions. All the spans are the same, right? So I guess with that, I put all the strips needed for all the slab design. So in practice, this is what we do. We need to identify all the spans. Now in our case here, I don't need to do all of that. I'm just going to be doing one of these. Are you with me? Following? So when I put here design one-way slab, I mean design just one strip. Take one strip here, do the analysis for it. You don't need to do all of them because this is going to be the same as this, same as this, same as this. So effectively, I have 3 typical slabs. This is going to be 1, this is going to be 2, this is going to be 3. But in our submittal, in our project, it's going to be only one of them, which means this guy here. I'm going to be doing only one. Following? Yes? No? Okay.
Why we're not adding the other 2?
Which other 2? This one?
Yeah.
Because I want to make it easier on you. So if you really want to do them, go ahead and do them.
No, okay.
All right. Okay. I have also this project statement. By now you should have it. This is an office building. It has 4 stories. The story height is going to be 12 feet. The code is going to be 2019 California Building Code. Soil bearing capacity, because eventually we're going to do foundation design, right? In the future. The capacity is 2,800 pounds per square foot. This is going to be the soil itself. Here's our scope of work, which means concrete design. We're going to have more than one element. And the first one is going to be one-way slab. And of course, we're going to have the columns and the whole thing. I mean, we're going to be doing the whole thing. Material properties. Now, if you like to consider here any material properties, please go back here. For the one-way slab or two-way slab, you consider 4,000 psi. So let me write this here. All right, it's going to be 4,000. So it looks to me that all concrete members, except for foundations, going to be 4,000. Only foundations going to be 3,000. And all steel is being grade 60, yield strength of 60 psi, right? Now someone's going to say, how about the loading? What loading should I consider? You're going to say, well, you have the self weight of the slab. This is what we call here dead load. So we have dead load and life load, right? So what is the dead load for you? Dead load is equal to, anyone remembers? Self weight of slab and beams, right? Plus what? Plus additional dead load. What is that for? You can say this is going to be for the flooring, for the ceiling below the floor, for mechanical ducts, light fixtures, and so forth, right? So you're going to have all of that. Okay? It's going to be additional 10 psi. So in order for you to find out dead load, you're going to say it's going to be equal to self weight of slab and beam, and then you add to it. We call this additional dead load. So let me write it here. Additional dead load. So final dead load, I'm going to say here, final dead load or dead load is going to be equal to self weight of beams, slabs, and beams. I'm going to say plus additional dead load. Where'd you get it from? Yes.
The additional dead load is just for like safety, correct?
No, it's not for safety.
No.
This is going to be weight for actual elements. Like what? I'm going to say mechanical ducts.
The fixtures,
cables.
The lighting.
Yeah, cables. Like what else? Fixtures.
Plumbing, ACT.
Yeah, whatever
flooring.
that you have in there, you just put it here, and then you assume here an average value of 10 psi. So you need to add it as an additional dead load. Now the partition weight, this is going to be actually a life load. Are you guys aware of this?
Oh, why is it a live load?
Because you can change it in an office.
Oh,
in office
okay.
environment,
So, like
you can change it.
cubicles.
So this is going to be life load. All right. If you're doing the floor itself, if you're doing floor design, like the second floor, the third floor, because it's going to be 4-story building, this is going to be the life load. The floor life load is 50 psi for an office. If you're doing roof design, it's going to be 20 psi. So for the roof, we usually do 20 psi. This is going to be for roof. And this one here, the 50 is going to be floor life load. Very good. So when you do here the floor, you need to add the partition weight to it as in life load. But when you do the roof, there's no partitions above the roof. Am I correct?
So you add. So it would be 65 per floor above floor 2, correct?
Correct. So let's say this is going to be the second floor. And here's the third floor. And here's the roof. This is what I'm expecting that you're going to be developing for us. And let's say that you have a column here. This is going to be your building, right? So when it comes to dead load, I guess you guys will figure it out. You need to know the slab thickness and then figure out the self weight of the slab and the beams and do the additional dead load. Now, how about the life load? I'm going to say life load here is how much? This is going to be what?
20 plus
20 psi.
plus 50, right?
Plus 50?
Oh no, just the 20.
Should I add some 15 like for partition? No?
No, since it's the roof.
Okay. How about here? You can see here is going to be 50 plus 15 psi. Here also is going to be 50 plus 15 psi. So now this is going to be what? This is going to be the life load.
And on level 1, Would it just be the 15 PSF?
In level 1, which means right here,
Yeah, so where the
this
foundation.
can be supported by the concrete slab and grade, so we don't design that.
Okay.
There's no design for it. You don't have to do any design. So this gave you your building, right? So let's see here the first submittal. What is that I need from you? It says here the submittal is gave you this Sunday for this course project as presented, develop the following. Load criteria for roof, third and second. Now a question, is there any difference between the third and the second when it comes to the load criteria?
No.
Okay, so it's gonna be one thing.
Mm-hmm.
So don't give me roof is gonna be different from the third, it's gonna be different from the second. No, I'm gonna have your two load criteria. All right? Load criteria shall include the details of the load. Where did you get it from? Find out the weight of the slab, right? Weight of the beam. How about the size of the beam? I don't have it yet. How about the size of the slab? I need to figure out something to start with, right? Now, I need to come up here with some assumptions. So I'm going to say the slab thickness, and look at this. This is what you're going to be using. Slab thickness is how much? And say equals 8 inches. Are you guys following me? Oh, someone's going to come back and say, I'm going to assume it 10 inches. I'm going to say, why? I told you just use 8 inches. Right? Why do I want everybody to have the same assumption? So this is going to be easier if I'd like to back check it. If you like to do to 10 inches, it's going to be just heavier and you're adding more material that you don't really need. So is this going to be the slab for the roof or the slab for the third or the slab for the second? All of them is going to be 8 inches. I'm going to say it's going to be for all of them. All right. Be sure when you want to start to work on this project that you go back to this recording on YouTube. All right. Slab thickness is going to be 8 inch. How about the beam size? Yes.
Are we going to have to account for the rebar also?
No.
Just
150 PCF.
Okay.
150. I'm going to say here unit weight
of
right?
concrete. Mm-hmm.
How much is it? 150 what?
PCF.
Pounds per cubic feet.
Yeah, what is that? Pound per cubic foot. Very good. This includes the concrete and the reinforcing. Everything all together. Any more questions on the loading? Now here's the question. How about the beam size? Because I give you the slab thickness, right? What beam size should we consider? I'm going to say for the beam size, for a beam like this, I'm going to say it's going to be 12 by, you can say by 18 inch. So which one is 12? Is it the width or the depth? Yes?
Could you repeat that one?
What is the 12 inch, the width or the depth?
The width, right?
The width, right, which is B. So I'm going to say it means B equals 12 inches. How about the depth? D, how much is D?
How
18.
long? Mm-hmm.
D, how much?
18 inches.
Is it D or F?
We have to look out at the table.
It's going to be H, right? You guys remember the difference between H and D? Anyone recalls the difference? H is going to be the total depth. It's going to be 18 inch, correct? It's going to be the beam size. The depth, you need to subtract the cover, right? And the diameter or the radius of the rebar. So now let me draw this for you. So here's the concrete slab, right? Where's the width? I'm going to say the width is going to be this dimension here. Let me go back to one of the slides. Yeah, like in here. Just borrow this from here so that I can use it here. I guess H is going to be from here to there, right? You guys agree or no? Not really. This can be what? This can be H. Meaning that this 18-inch is going to include the 8-inch, which is slab thickness. This slab thickness, it's usually referred to H sub S. Some people would call it T sub S. Slab thickness, right? It's going to be equal to 8 inches. So the distance from here to there is going to be 8 inches. And the total depth of the concrete is going to be what? 18-inch. This is going to be H, right? This can be kind of tricky when you do the weight of the beam, right? Because when you do the weight of the beam, do you want to consider this box here as one beam and then call it to be 18-inch, and then the slab is going to be continuous? Or when you do the weight, you're going to consider the slab to be continuous, and then you say, in determination of the weight, I need to use this depth. And how much is this depth now?
10.
It's going to be 10 inches. How about the width B? Where is the width B? I'm going to say width B is going to be this width here. So let me put it right here. This is going to be your width B, and this is going to be equal to how much? This is going to be B, 12 inches. So, okay. So I guess now we know what to do when it comes to load criteria. And at the end, you need to find out W ultimate, and W ultimate is going to be 1.4 times dead load versus 1.2 dead plus 1.6 live. So we know this load criteria is going to be included in here. Now the second item needed is say design a typical one-way concrete slab at the roof and typical floor.
Excuse me.
Yes.
Is it going to be the same thing for the girders also?
Yeah, girders is going to be the same size. All beams is going to be like this size.
Okay.
Now, when I do here the load criteria to design the slab, is the slab supporting the beam? Or the beam supports the slab?
Beam supports this slab.
So when I do design here for the slab, which weight should I consider? Should I consider the weight of the beam, or weight of the beam is going to be considered when I design the beam?
When you design the beam?
Only when you design the beam, which means if you're like here to do analysis for the concrete slab and design of the concrete slab, do not consider the weight of the beam. So I'm going to have separate load criteria for the slab versus the beam. Make sense?
Could you repeat that just one more time?
Okay. So I'm going to have here load criteria. One of them, so I'm going to say here, I'm going to have two sections, right? One of them is going to be for the slab design. So I'm going to say for the slab design, say slab design. Should I consider the weight of the beam? I'm going to say no.
No.
Slab weight only. Another question. Would I consider the additional dead load? Say yes. For the slab design is going to be slab weight only. I'm going to say plus additional dead load. And of course, the life load is going to be there. But when it comes to the beam design, you can see here beam design, right? So you can say in beam design, I'm going to say slab and beam weight. So beam weight plus additional dead load. The thing is going to be recorded, and you can go back to it when you want to work on this. So which slab are you going to be taking? I'm going to say you just take one strip. Now where is this one strip? You see this guy here. Just consider this one, please. It's going to be 9 spans. Supported on lots of supports here. How can I do the structure analysis? Well, this is going to be like same span. There's lots of structure books. Gives here continuous beam, equal space or equal span, and you can figure out the moment, top and bottom. What do I mean moment, top and bottom? For this beam here, which is a slab, you're gonna have negative moment and positive moment. Can you guys help me? What moment would I find here? It's gonna be like in the middle of the span. It's gonna be positive or negative? The middle of the span. Right here, you're gonna have positive moment. How about here, on the top of the concrete beam? Let's see M, negative. which means I'm gonna have top reinforcement and bottom reinforcement. Make sense?
So you said that the bottom of the
Yeah.
bottom of the beam would be positive moment. Okay, and then the top would be negative moment, correct? Okay, thank you.
Now, if you consider that you're taking a section here, let's say here's a section of the slab, right? Which is this one here. I'd like to provide here some reinforcement. I'm gonna say, here's a section of it. Thickness is gonna be 8 inches, right? Now, I'm gonna have reinforcement, top and bottom. Where's the bottom reinforcement? I'm gonna say it's gonna be right here, right? Bottom reinforcement is gonna be like this. Top reinforcement is gonna be right here, correct? Here's the top reinforcement. Now, in the middle of the span here, which means at this location, do you have tension the top or the bottom?
I want to say at the bottom.
The bottom, yeah, it makes sense. Why? Because this is where we have the positive moment.
Right.
Beam wants to sag this way. And here is giving the top of the beam. You're going to have negative moment, correct?
Yes.
Yes, okay, good. Yeah, second here. Here's the concrete slab that I'm talking about, one-way slab. The strip here is going to be 1 foot. It's going to be considered to be a beam that spans from a beam to a beam to a beam, right? So direction of carriers. This is going to be the load direction. And here is, let's say, consider this to be the slab for a second. Just ignore whatever that you're looking at. In the top of support, you're going to have cracking. Why? Because you have negative moment, and here you have negative moment. In the middle, tension is going to be at the bottom, right? Because you have here positive moment. Very similar idea here. This is going to be in the middle of the span. You're going to have here some cracking. This is where you need to have the reinforcement. And here in the top, you're going to have negative moment, and this is where you need to provide reinforcement on the top. So I'm going to say here, I'm going to put a statement. I'm going to say AS top. What is AS top for? For M negative, correct? And say in this case, I'm going to have AS bottom for M what? Positive moment, M positive. Make sense or no? So in your beam analysis, you need to look for the maximum moment at the bottom, right? Maximum moment here at the bottom. Just take it and design the section. Are we good? Questions? Same thing for the top. Top, you're going to be looking here for the maximum negative moment, and then you design the negative or the top reinforcement for it. Questions?
Is there gonna be weekly questions like you're gonna post on Sunday?
Weekly questions, what do you mean?
You mentioned that we have to find the dead load calculations as the submittal. Will there be multiple submittals throughout the semester?
Yeah, it's going to be more than one submittal. This is going to be the first submittal, as you see here. This submittal is only for the slab design and the load criteria. You're going to have the column design, you're going to have the beam design, you're going to have the foundation design, we're going to have also wall design. So this is going to replace the homework. And instead of giving you this as a homework, right? I'm just doing it here for the same plan. So when you look at this plan here, you say, okay, we are trying here to put this building together, and here's the design of the slab, right? And then when it comes to beam design, I'm going to be asking you to do here B1 and B2 only. And then later on, we're going to be doing this wall only. Then we're going to be doing a footing below this column only. We're going to be doing only a few column design here, right?
Right.
So it's going to be all related to each other. And instead of just give you here separate homework, and you don't feel that they're interconnected to each other. All right, questions, or should I let you go?
So for this first submittal, we're just focusing on the loading and we're using the slab thickness and the beam dimensions that you gave us, that we just assume those?
Yes, consider that in your analysis.
Okay, thank you.
No problem. Are you good?
Professor, for depths of the beam, do we choose the depths ourselves?
I give you here some numbers to start with, and they should be good for your analysis. For the slab, it's gonna be 8.
There is no cover, but there is no cover, so
There's
we do
what?
not know the depths. The concrete cover.
Oh, when it comes to the actual depth, you mean D?
Yes.
Okay. For D, you can take the cover to be 2 inches, and then you have the tie diameter, and then you have 1/2 of the bottom reinforcement diameter. So when it comes to beam design, we can discuss it again. So I'm going to say subtract 2.5 inches. So generally speaking, if you're doing a design like this, let me put it here for you. It's going to be D equals H minus 2.5 inches. If this is going to help you. How about the cover for the slab, right? Someone's going to say, no, the slab thickness is 8 inches. What does it mean by 8 inches? The entire slab thickness, right? How about for D of the slab? I'm going to say here, D for the slab. Okay? Is equal to 8 inches minus, going to be taking it let's say 1.5 inch. 6.5 inches is going to be the depth of the slab. And this depth here is going to be depth of the beam. It's going to be H, which is 18 inch minus 2.5.
So for slab, the D prime is also 1.5.
Which one?
The D prime. It's the bottom steel bars.
D prime for the top compression reinforcement. Yes. Yes. It's going to be 1.5. 1.5 is good, or 2 inches is good. All right.
Are we taking the slab thickness now to be 6.5 inches instead of 8 inches?
No, this is H of the slab, and this is D of the slab. All right, let me draw this for you. Let's say here's the slab, right? Where is the reinforcement? I'm going to say reinforcement is going to be right here. Right? What does it mean by H? H is the total depth of the slab. So let me copy this here to there. Good that you asked me this question. Thickness of the slab is going to be from here to there. Right? How about depth of the slab? I'm going to say depth of the slab is different. This is depth of the slab is going to be from here, the top compression, to the center of the rebar. And this is going to be what? This is going to be D for the slab. Depth. So this here D, right? Of the slab to the center of the rebar. This is going to be H for the slab. Are we clear now about difference between depth and thickness?
Mm-hmm.
Okay, good. All right, great. More questions?
Professor, this is with partners, correct?
This is what?
Group project? Or this is individual?
No, individual.
Individual?
Yeah.
Okay.
I'm sort of confused. So the submittals portion is individual, but overall this is a group project, or is it just all solo?
This is to replace the homework.
Right. Mm-hmm.
So when it replaces the homework, it's going to be individual. It is not group project.
Okay.
It is okay to communicate with others and see what they're doing and discuss it with them, but everybody's gonna have a separate submittal. But please don't just copy and paste the answers from someone else. Because in this case, I'm gonna assume that someone is cheating from the other one, right?
Mm-hmm.
So you don't wanna do this. And for that, you have no homework, right? Because I'm gonna stop the homework and put instead, I'm gonna have this course project. Very good, clear?
Yep.
All right.
Yes.
All right, so go ahead and sign out unless you have questions, stay around.
I've got another question. In the layout, how do we confirm that this is a one-way slab? I'm looking at the dimensions and I know that it's L1 over L2. In this case, L1 is 26 feet.
Yes.
And then L2 is about 9.3 feet. I'm dividing 28 by 3.
Yeah, hold on.
Okay.
Give me a sec here. We call this L and B. Someone's gonna call it LX, LY, which is fine, you know. So this length is 28 feet, right? This bay for this bay here is gonna be 28 feet, 26 feet, by the width of it, which is 9 feet and let's say about 4 inches or 9 feet. So 26 divided by 9 is how much? Is it more than 2? You say yes, of course. You have up to 13 feet for the slab span to make it one way. So we should be fine. This is one-way slab.
Okay, thank you.
No problem. Thank you.
Professor, do we do the calculations on Excel, or does it not matter if it's between Excel or hand drawn on paper?
Okay, here's the issue when you do Excel. Absolutely, I have no problem with Excel. But I want you to listen at this carefully because I don't want to just reduce points here for you. When you do Excel, you need to develop a PDF. So your submittal is going to be in PDF. You need to show me how you calculate out, right? Where's the equation? How did you do the weight?
Oh, I see.
So if you like, you can type everything in Excel and do also something else in Excel, but be sure that you put the equation, right?
Okay, yeah, because if you do PDF, you won't see the formula.
So I have no problem if you want to use Excel, but be sure that you show the equation. You need to type it.
Okay. Thank you.
No problem. Thank you. All right, you guys, you have a good night.
Thank you, Professor.
Thank you.
All right. Okay, bye.